Hey, what's up, guys? It's G the Chemist here with a discussion on physics. And in this video, we're going to be going over inflation theory. And so, before Edwin Hubble's observation, Einstein, as well as the physics community, believed in a static universe and that the universe was not changing. And so, in 1917, Einstein added in a cosmological constant to his theory of general relativity to force the equations to predict a static universe. Einstein, he later found out that this was not true and that the universe was not static, and he called this his biggest blunder. But recent developments have actually revived Einstein's cosmological constant, and Einstein's biggest blunder is now helping physicists nowadays. We'll talk more about that later in the video. And so this brings us to Georges Lemaître, and Lemaître was a Belgian Roman Catholic priest. He obtained a PhD in physics and mathematics, so he had two PhDs. And in 1927, after reviewing Einstein's mathematics from his theory of general relativity, Lemaître proposed that the universe could not be static and that it is actually expanding. And Lemaître also proposed that the universe could have only came to existence from a single very dense point that exploded and expanded. And this infinitely small point that the universe originated from, he called it the primeval atom. And this was later called the Big Bang theory. And obviously a lot of religions and religious people don't like the Big Bang theory, but it was actually proposed by a Roman Catholic priest. So I thought that was pretty interesting. And so with Edwin Hubble's observations, Edwin Hubble was an American astronomer, and he proved the existence of other galaxies. But in 1929, he concluded from observation that the universe was in fact expanding, and he did this by finding that galaxies that were further away were accelerating faster than closer ones. And from this he formed Hubble's law, which is that the greater the distance between any two galaxies, the greater the relative speed of separation. And a good way to visualize this is to think of a loaf of bread baking with raisins inside. And as the bread bakes in the oven, the raisins get further and further away as the bread expands, and raisins further away separate faster because there is more bread in between them expanding. And so from this there was a quick a theory that was around for not too long. It got refuted very quickly, but it was the cyclic universe theory. And the cyclic universe theory was a model of the universe that says that the universe goes through infinite cycles of expansion and cooling, or a Big Bang and Big Crunch. And a lot of physicists like this idea, including Einstein, but it was short-lived due to the work of Richard Tolman in 1934. And Tolman showed that the cyclic universe theory violated the second law of thermodynamics, which states that entropy can only increase. And his work also showed that the universe could only expand larger and larger, and because of this, the cyclic theory lost support and was refuted. And so there's something called the microwave background, cosmic microwave background, which is it's leftover radiation from the Big Bang. And the Planck telescope mapped out the cosmic microwave background and found the fluctuations in it. And this was a problem because the expansion model of the universe predicted that the cosmic microwave background would be consistent and uniform throughout, and this caused problems for the expanding universe theory. And now we need another model for the evolution of the universe to explain these fluctuations. And not only was there the problems with the fluctuations in the cosmic microwave background, but there was also the horizon problem. And the horizon problem is a problem of information communication, and it seems that information was communicated faster than the speed of light, because due to the size of the universe when the cosmic microwave background formed, the universe was only 300,000 years in light years in diameter. And I should mention that often in physics and cosmology, distance is often measured in time, because time is a variation of distance shown by relativity. But anyways, with the horizon problem, when the cosmic microwave background formed, the universe was only 300,000 light years diameter. But now there is the universe is 13.7 billion light years, and so we shouldn't have been able to receive the information from the cosmic microwave background, because there has not been enough time for the information to reach us. And so this implies that the information traveled faster than the speed of light. And so because of this, in 1980, the theory of cosmic inflation was proposed by Alan Guth of MIT. And inflation theory solved both problems with the fluctuations in the cosmic microwave background as well as the horizon problem. And Guth proposed that for about 10 to the minus 35th of a second, the universe inflated by a factor of 10 to the 26th. So during this period of inflation, the universe went from smaller than the size of a proton to about the size of a grapefruit in 10 to the minus 35th of a second. And the universe inflated faster than the speed of light. And so the information in the horizon problem did not actually travel faster than the speed of light through space, but with space as it inflated. And this also explains the fluctuations in the cosmic microwave background, because the universe, well, space inflated faster than the speed of light, faster than the universe itself could compute what was going on, and it sort of lagged a little bit, causing fluctuations in the cosmic microwave background. So cosmic inflation theory not only solves the horizon problem with how we have access to this information where we shouldn't, but it also solves the fluctuations that we see in the cosmic microwave background. And so what caused this rapid inflationary period? There's still not a clear answer as to what caused the universe to inflate so rapidly, but the leading answer or leading hypothesis, I'd say, would be due to positive vacuum pressure. And this positive vacuum pressure is hypothesized to result from the separation of the strong nuclear force from the elementary forces, since this happens about the same time that inflation occurred during the evolution of the universe. And this caused a phase transition, which left the universe highly unstable, because it now had so much energy than it would have at this point, causing a sharp anti-gravitational effect, causing it to inflate very rapidly. And so why does the universe still continue to inflate even now? And the reason for this is due to the presence of dark energy. And dark energy is a form of energy which has repulsive gravitational effects that permeate space. And dark energy accounts for 74% of the total mass energy of the universe. And the name dark energy was given to reflect our current ignorance on it. And understanding dark energy will be very important for modern development in these theories. And this brings us back to Einstein's cosmological constant, and this is where Einstein's cosmological constant and biggest blunder was actually revived. And recent developments have shown that his cosmological constant was a perfect fit for dark energy, and this was because when he was calculating the energy needed to predict a static universe, he was actually calculating for dark energy. And so even Einstein's biggest blunder is still helping us to this day understand the universe, which is pretty wild. And so this brings us to the shape of the universe, or what this means for our shape and curvature of space. And so this can be calculated by omega, which is a ratio of the universe's density to the critical value to stop the expansion of space. And there are three potential shapes of the universe, which is spherical when omega is greater than 1, hyperbolic or open, which looks like a potato chip, with omega being less than 1, and then a flat universe with omega equaling 1. And our universe appears to be flat since our density to critical value has a ratio of 1. And this has been met with some criticism, especially by Guth, because Guth claims that the universe appears to be flat since we can only observe a small bit of it, just how the Earth looks flat from the ground. And so with the cosmic horizon, Guth's calculations for the inflationary model predicts that the universe is actually 10 to the 23 times larger than the observable universe that we can actually see. So there's much more out there than we can actually observe or have the information to us. And so if you were to think about this, it would be if our observable universe was the size of the planet Earth compared to the observable universe now. So that's obviously pretty small in comparison. If you compare the size of the Earth to the whole universe, it's incredibly tiny. But our observable universe to the size of the Earth would be equivalent to the ratio of what we can see to what's actually out there. And we are unable to obtain information from most of our universe since not enough time has passed for the information to reach us. And this is also why we appear to be in the center of our universe, because we can only observe 13.7 billion light years in our universe in all directions, even though the universe is much larger than what we can actually see and have access to. And so with all this, how will our universe end? And our universe will most likely end in a big freeze. And this is because as the universe expands, everything inside of it will travel further and further away from each other until everything is infinitely far away from each other. And this is because physicists calculate that dark energy will win the fight over gravity, causing an infinite expanse. But luckily for us, this will not happen for another 50 billion years. So we have another 50 billion years of our universe being good for us. And so that does it for inflation theory. I'll definitely be doing some more physics videos, probably some on string theory and M theory, and some more stuff. So Be looking out for those. So that does it for this video. See you guys in the next one.